In this video lecture, we will introduce the Kirchhoff's laws for currents and voltages in a circuit. The expression Kirchhoff's law for currents is abbreviated to KCL, acronym for Kirchhoff's current law, while the expression Kirchhoff's law for voltages is abbreviated to KVL, acronym for Kirchhoff's voltage law. The Kirchhoff's law for the currents in a circuit, also known as the Kirchhoff's law at the nodes of a circuit or as the first Kirchhoff's law, can be directly derived from charge conservation principles. Kirchhoff's current law states that the algebraic sum of the currents entering the node of a circuit is zero. By node in a circuit, we mean a point of the circuit where two or more components connect together. As an example, let us consider a node A in a circuit where 5 branches connect together. In this example, 3 branches are represented by resistors, one other branch is represented by a capacitor, while the fifth one is taken by an inductor. You may not know yet how an inductor or a capacitor work, but this is not important. We will be discussing about their properties later on during these video lectures. In the network in the figure, let us consider the currents flowing through each of the 5 branches. So we will have current I1, current I2, current I3, current I4, and current I5. Each of the currents will have a direction. So for example, I1 and I5 and I4 point towards node A, while I2 and I3 flow out of node A. In stating Kirchhoff's law for currents, I use the expression algebraic sum of the currents. By algebraic sum of the currents, we mean the sum of the currents each with its sign. The sign of the current will depend on a preliminarily adopted convention on the current direction in the circuit. For instance, we can assume that the current is positive if it enters the node. In this case, for the network on the left, Kirchhoff's law for currents, we say that I1 minus I2 minus I3 plus I4 plus I5 is equal to 0. More generally, if we have n branches connected to a node, then Kirchhoff's law for currents will state that the sum for I going from 1 to n, where n, as I said, is the number of branches connected to the node, sum of I sub I will be equal to 0. It is intended here that I sub I will have a sign depending on the convention adopted for the currents. It is easy to demonstrate that the result we obtain does not depend on the adopted convention. This means that even if we adopted the opposite convention, which means even if we assume positive sign for currents exiting the node, Kirchhoff's law for current would yield exactly the same result. Note that in the network in this example, the charge entering the node A through currents I1, I4, and I5 must be equal to the charge exiting the same node through currents I2 and I3. This is a charge conservation principle which is reflected by Kirchhoff's law for currents. Let us consider two resistors in series. Two resistors may be defined as being in series if they have one single terminal in common. Let us call this common node B. Let's define I1, the current flowing through resistor R1, entering node B, and I2, the current flowing through resistor R2, exiting node B. Based on Kirchhoff's law for currents, we can write that I1, current entering node B, minus I2, the current exiting node B, is equal to 0, from which we get that I1 is equal to I2. So Kirchhoff's law for currents in a circuit tells us that the current flowing through two resistors in series is the same for the two resistors. This result will be extended to capacitors and inductors in series. We'll be discussing about that later on during these video lectures. We can, of course, have more than two resistors in series. Also, in that case, the current flowing through these resistors will be the same. Kirchhoff's law for voltages in a circuit, also known as Kirchhoff's law for loops in a circuit, or second Kirchhoff's law, derives from the fact that the work needed to move a charge from one point in a circuit to the same point is 0. So let us consider a closed loop in a circuit, and let us define a conventional direction of travel around the loop. By closed loop, we mean a circuit or part of a circuit where a charge moving from any point in the loop can get back to the starting point without changing the direction of its motion. The second Kirchhoff's law states that the algebraic sum of the voltages across each of the branches of the loop is 0. By the way, a branch in a loop is the part of the loop between two adjacent nodes. The loop in the figure has 5 branches. Let's define the voltages across the 5 branches as V1, V2, V3, V4, and V5. Let us assume that the voltage is positive if its direction is opposite to the conventional direction of travel, negative otherwise. Therefore, based on Kirchhoff's voltage law, we can write that V1 minus V2 minus V3 plus V4 plus V5 is equal to 0. This result can obviously be extended to the case of a loop with a number n of branches. In this case, Kirchhoff's voltage law we read as sum for I going from 1 to n, where n is the number of branches, of V sub I is equal to 0. Where, of course, V sub I will have to be taken with the correct sign according to the convention adopted for the loop. Of course, the result provided by Kirchhoff's voltage law will not depend on the convention adopted for positive and negative voltages in the loop. Two resistors are said to be in parallel if they have both terminals in common. The two resistors R1 and R2 in the figure makes up a loop. Let us define a conventional direction of travel in the loop. Let's call V1 the voltage across R1 and V2 the voltage across R2. Based on Kirchhoff's law in this loop, V1 minus V2 is equal to 0. Therefore, we get that V1 is equal to V2. So, Kirchhoff's law for voltages tells us that resistors in parallel have the same potential drop across them. This result will be extended to capacitors and inductors later on in these video lectures. We can have, of course, more than two resistors in parallel, and also in that case, the voltage across these resistors will be the same. Let us consider now this circuit consisting of a battery providing a voltage difference E with its negative terminal connected to the ground reference, and two resistors R1 and R2 in series, with the second terminal of R2 also connected to the ground reference. Note that the two ground references here represent the same node in the circuit. This means that this circuit is exactly the same as this circuit. Note that the battery and the two resistors are in a series connection, so this means that the same current I will flow through the resistors and will come out from the positive terminal of the battery. Let us now define a conventional direction of travel in the loop. Let us also define the voltages V1 and V2 across the resistors R1 and R2 respectively. According to Kirchhoff's law for voltages in this loop, we can write that V1 plus V2 minus E is equal to 0. On the other hand, according to Ohm's law, we can write that V1 is equal to I R1 and that V2 is equal to I R2. If we replace V1 and V2 in the first equation with their expression as a function of the current I, we get I R1 plus I R2 equal to E, or I R1 plus R2 equal to E, from which we get that the current I provided by the battery E to the load consisting of the series of the two resistors R1 and R2 can be written as E divided by R1 plus R2. So, as far as the current I provided by the battery is concerned, the two resistors can be replaced by a single resistor Rs, whose value is equal to the sum of the resistances R1 and R2. Rs is called the equivalent resistance for the two resistors R1 and R2 in series. So in this case, the current I can be expressed as E divided by Rs. So two resistors in series, R1 and R2, can be represented by means of an equivalent resistor with resistance Rs equal to R1 plus R2. This result can be extended to any number of resistors in series, R1, Rn, and in this case, the equivalent resistor will have a resistance Rs equal to the sum for I going from 1 to n of R sub I. Consider now this circuit, including a battery, generator, as I said, the three components are in parallel, so the voltage V1 across the resistor R1 and the voltage V2 across the resistor R2 are both equal to E. This, as we know, is a consequence of the second Kirchhoff's law. Now, let us consider the current I flowing out of the positive terminal of the battery and the current I1 and I2 flowing through resistors R1 and R2 respectively. Let us apply Kirchhoff's law for currents at node A in the circuit. According to Kirchhoff's current law, assuming that the current is positive if entering the node A, we can write that I minus I1 minus I2 is equal to 0. On the other hand, Ohm's law tells us that I1 is equal to V1 divided by R1 and I2 is equal to V2 divided by R2. If we replace I1 and I2 in the KCL equation with their expression as a function of V1 and V2, we get I equal to V1 over R1 plus V2 over R2, or given the fact that V1 and V2 are both equal to E times 1 over R1 plus 1 over R2. So as far as the current I provided by the battery E is concerned, the two resistors R1 and R2 in parallel can be replaced by a single resistor Rp whose value is given by 1 over R1 to the minus 1 plus R2 to the minus 1. Rp is called the equivalent resistance for the two resistors R1 and R2 in parallel. So in this case, the current I can be written as E divided by Rp. Therefore, two resistors in parallel, R1 and R2, can be represented by means of an equivalent resistor Rp, whose value is given by 1 over R1 plus 1 over R2, or R1 times R2 divided by R1 plus R2. This result can be extended to the case of the parallel configuration of n resistors, R1, R2, Rn, and in this case, the equivalent resistance Rp will be given by 1 over the sum for I going from 1 to n of 1 over R sub I. The parallel between two resistors R1 and R2 is indicated with this symbol or this other symbol. Note also that if R1 is equal to R2, equal to R, then the parallel between R1 and R2 is equal to R squared divided by 2R equal to R divided by 2. So the parallel between two equal resistors is half the value of each of the resistors. Let us consider now this circuit including a battery and three resistors. The voltage E is equal to 10 volt. The resistor R1 has a resistance of 5 kilo ohm. The resistance R2 is 4 kilo ohm, and the resistance R3 is equal to 12 kilo ohm. We would like to find the current I flowing out of the positive terminal of the battery E. This current can be easily calculated if we are able to replace the complex network R1, R2, and R3 with its equivalent resistance. In general, an electrical network consists of a number of components which are neither all connected in series nor all in parallel, but some subsets of them may be. To these subsets of components, we can apply the rules for computing the equivalent resistance, therefore reducing the network complexity. In this circuit, for instance, R2 and R3 are in parallel, so we can replace them with the equivalent resistor. In particular, the equivalent resistance REQP for the two resistors R2 and R3 in parallel will be given by R2 times R3 divided by R2 plus R3, which is 4 kilo ohm times 12 kilo divided by 16 kilo. And this is equal to 3 kilo. The resulting simplified network will consist of the battery E and the resistors R1 in series with the resistor REQP. Note that from the point of view of the battery, the load has not changed. We just replaced part of the network with its equivalent resistance. Now, as I said, R1 and REQP are in series, so we can replace them with the equivalent resistance REQ equal to R1 plus REQP, according to the rule for reducing resistors in series. REQ is equal to 5 kilo plus 3 kilo, or 8 kilo. Eventually, the network can be reduced to a much simpler one, consisting of the battery E and of a resistor REQ. This resistor REQ is the equivalent resistor for the network made up of the resistor R1, R2, and R3 in the original circuit. Now the current flowing out of the positive terminal of the battery E can be easily calculated by applying Ohm's law as E divided by REQ, which is 10 volt divided by 8 kilo, which is equal to 1.25 milliamps. Solving an electronic circuit means calculating all the currents in all the branches and all the potentials at all the nodes in the circuit. Kirchhoff's laws, together with Ohm's law, are the necessary tools to perform circuit analysis. Consider, for example, this circuit, including a battery, 4 resistors, and 2 loops. In order to fully solve the circuit, we need to find the currents I1, I2, and I3, and the voltages V1 across R1, V2 across R2, V3 across R3, and V4 across R4. So we have 7 unknowns, and in order to find them, we need 7 independent linear equations. 3 of these 7 equations are provided by Kirchhoff's laws for currents and voltages in the circuit. In particular, we can write the equation for the currents at node A as I1 equal to I2 plus I3. Then, choosing the conventional direction of travel in loop number 1 and in the second loop, we can write the Kirchhoff's equations for voltages E equal to V1 plus V2 and V2 equal to V3 plus V4. The remaining four equations we need can be found by applying Ohm's law. In particular, we can write that V1 is equal to I1 R1, V2 is equal to I2 R2, V3 is equal to I3 R3, and V4 is equal to I3 again, because R3 and R4 are in series, times R4. If the values for the voltage provided by the battery E and for the resistances R1, R2, R3, and R4 are given, then the resolution of the system of 7 equations provides us with the values of all the voltages and the currents in the circuit.